This week, the topic of this round is clustering. So clustering is an unsupervised learning method where unsupervised means that we don't have any label data. And the idea is to find a way to group data points based on how similar they are, or well, more specifically, how similar their features are. And some examples of that. So probably the most common example is how advertising companies segregate their customers or clients and make groups of people and then recommend products to a certain type of person and so on. So yeah, this is clustering used in market research. Then another common thing where clustering is used is image segmentation. You can think of that also as minimizing the size of the image. So for example, we would cluster or group the colors of the image that are similar, and then we would substitute the similar colors with the centroid or with like the mean of these similar colors. And this way we can get a smaller size of image. Yeah, and then recommendation systems for movies or again, products or whatever. So clustering is typically divided into two categories. We have soft clustering and hard clustering. And the question that hard clustering tries to answer is, does a data point belong to a cluster? Why? So the answer is always yes or no. While on the other hand, soft clustering asks the question, how probable is it that the data point belongs to a cluster? So each data point has a probability of belonging to a certain cluster. Yeah, and we will also discuss about DBSCAN, which is a density-based clustering algorithm. And yeah, it's also hard clustering. And then we will also see the problem.
Yeah, K means probably the most popular clustering algorithm. And then we will also see GMM, Gaussian mixture models for soft clustering. So the learning goals are learn how to use K-means, learn how to use GMM and DBSCAN. Yeah, and how to choose between different clustering methods and different number of clusters, because typically you also have to decide on how many clusters you are expecting. Okay, let's start with the basics. So assume we have m data points denoted by x. The task is to assign its data point to one of the k groups. So k here is a hyperparameter which means that we are the ones that should define it. And yeah, to define a clustering algorithm, we also need a similarity function. So a data point xi, how similar is it to data point xj? So if they are too similar, then maybe they belong to the same cluster. Yeah, and now since we don't have any labels, you can understand that it's not so easy to evaluate how good a clustering algorithm is, or the outputs of the clustering method are. Yeah, and we will see different ways of how to counter that. So K-means is a hard clustering method that works following this pseudocode. So we first initialize some centroids. Yeah, I will show this animation first and then go to the algorithm. So as you can see here, we first initialize these four centroids. And then we calculate the similarity or the distances to each and every other of the data points. And then as you saw from here, the centroid changed to here. So this is like the middle point of all of these data points, of all of these similarities. So we want the centroid to be at the center of all of the rest of the data point. So um, yeah, if you have any questions about this, feel free to ask them. But I will go to the pseudocode. Maybe it's easier this way. So here M denotes these 4 data points we saw before, and then while we haven't reached convergence, so while true, we assign the data points to the closest centroid. So for each data point in our data set, we calculate the similarity to the centroid, to one of the random starting centroids, and we assign it to the closest one. And then, yeah, so for each data point, we calculate this. Yeah, and this is the similarity function used in k-means. So this is a Euclidean distance, simply the norm 2 square. Okay, and then we update the means by averaging samples in each cluster. So we're practically averaging the distances, and we take the mean one. And then our convergence check is that if the means have not changed in a while, then there's probably no reason to go on. So yeah, we break the loop. Okay, so a good thing about k-means is that even though it's simple, it is guaranteed to converge. So we will not have like an infinite loop that doesn't end. However, it might converge to a local minimum. So it is not always guaranteed to find the best possible centroids. And there are certain techniques to help us avoid such cases. A common one is to try out different starting centroids, because as you saw in the animation, the starting centroids are usually initialized in a random way. So if you do that random initialization many times, then you may get different results every time. So you will see like the local minima. If you see different local minima, then one of these must be the global optimum, most probably, if you do that many times at least. Okay, then another common technique is, yeah, so this is exactly what I said now, sorry. And when implementing this in scikit-learn, you need to make sure that you set this number of utilizations to 1, because in the assignment you actually have to implement the for loop, like the initializations yourself. Yeah, there are instructions there, but make sure that you know of this and init parameter. Okay. Yeah, now, as we mentioned, choosing the number of clusters is a hyperparameter that you are the ones that have to choose. So how can you know which one is the best number of hyperparameters? Well, we will again use the validation set that we introduced before, and we will try out different k values, and we will pick the one that has the smallest error on the validation set. And yeah, and to pick the one, we typically use the elbow method, which will be shown in the next slide. But let's first discuss about what's the error. So the error is just summing the Euclidean distances of its data point. So we want this sum to be, well, ideally we would want this to be 0, but that's not possible. So we would want these distances to be like small, the smallest possible. Yeah. Again, if you have any question, feel free to interrupt me. So if the majority of data points are far from the centroid, then the error will be high because the individual Euclidean distances will be very high. Okay, now let's see the elbow method. So Here this is taken from the assignment. We tried out different values of k, so from 1 to 8 different clusters, and um, the elbow method says that the the best possible number of clusters is the one at the elbow point of the plot. So it's the point where the error starts decreasing in a linear function. So here it will be between 3 and 4, because after 3 this seems to be like a straight line. After 4 this is even more obvious, so this will be up to you, but yeah, personally I think that 4 may be the best number of clusters. Okay, if you have any questions about k-means, okay, assume not. So let's move to soft clustering then. So yeah, with hard clustering, it is not possible to see how probable it is that the data point belongs to another cluster other than the one that we assigned it to. And well, that's not really what we always want. We we ideally want to be able to assign a probability for each and every cluster. And in soft clustering, we actually assign a confidence score. So, for example, in this plot, the data points that are inside the circle have a high confidence score. So, like the algorithm knows that these data points do belong in this cluster, but the data points outside the circle could belong to another cluster. So that's what this says to us. Or they could even be outliers. So you could use this sort of methods to simply discard bad examples in your data. Right. And Gaussian mixture models are probably the most common way to perform soft clustering. So as we said, we assign probabilities. So instead of assigning a data point to one class, we are now assigning scores in a class, in a vector of classes. So its yi would contain a score that the ith data point belongs to the first class, and so on. Okay, and in the GMM, we assume that the data are drawn from k different Gaussian distributions, and each distribution is parameterized by its own mean vector and covariance metrics. So we will not get into many details about the Gaussian distribution or how we update the mean and covariance metrics. But in the notebook, there is a small optional section if you are interested in that. And yeah, so our task is to find the best mean and covariance metrics. And we also want to find the best probability assignments that correspond to these means in the covariance metrics. So we denote the assignments by the pi, and C is the ID of the cluster. So this is the multivariate Gaussian distribution. Oh no, that's the one-dimensional one. So yeah, as you can see, by tweaking the mean and the variance, we can have many different distributions. Like the tails are either more flat or yeah, the whole graph is wider, and so on. So yeah, each one of these separate Gaussian distributions could denote a separate cluster, for example. Some drawbacks of GMMs are that it's usually slower than K-means. I also have to add here that it's kind of more complex, maybe, for someone without a probabilistic background. And it uses the expectation maximization algorithm, which may not be so easy to familiarize yourselves with if you don't have the necessary background. But in any case, you will not need that in this course, so you should be fine. Yes, and also it is very heavily dependent on the initial values of the parameters. And then if the measure is not a Gaussian distribution, so if the underlying distribution is not Gaussian, then the GMM soft clustering will not work. Right, and it is also like K-means, it can also convert to a local minimum instead of a global minimum. And we can try out the same approaches as with K-means to get over this issue. Yeah, let's also see another animation of that. So as you can see here, the wider the circle is, the more, no, sorry, the denser the circle is, the more probable it is that the data points there belong to the certain cluster. So as you can see with the yellow data points, when it converges, there are these yellow data points that don't seem to be probable at all to belong to that cluster. So maybe we could consider them as outliers or still accept them. Yeah. And then there is this page with documentation about clustering from scikit-learn, and they have this really nice image, which I will show you later. And also this 7-minute lecture on expectation maximization is a very good one if you are interested to learning more about how GMMs work, like underlying all that. But again, you will not need to implement the algorithm itself. scikit-learn already has it there. So, any questions about GMMs? Okay, then maybe, yeah, we will move to density-based clustering and DBSCAN in particular. So the methods we have seen so far both use the Euclidean distance to measure similarity and the error. But in many cases we don't have a Euclidean structure, and these algorithms tend to fail in such cases. So what density-based clustering does is it reformulates the problem into a graph theory problem, and it uses the connectivity relation to define similarity between data points. So two data points are considered connected if one carries the other by intermediate data points. And if those intermediate data points have a small Euclidean distance among them, then we can say that the node at the start of the path and the node at the end of the path are similar. So for example, here, this is also taken from the notebook. With the classical Euclidean similarity measure, you would say that these two are not similar, just because the Euclidean distance, which is this line here, is kind of large. But on the other hand, when using connectivity to define the similarity, we see that from this data point we can jump to the next one, then to the next one, to the next one, and then to the last point. So these distances are pretty small, which means that probably these two data points are similar. So these two data points are similar, and so we assume that the first and the last one are similar too. Yeah, so that's like the big picture of how DBSCAN works. Um, so again, it's a hard clustering method. So a data point either belongs or not to the corresponding cluster. And another good thing about DBSCAN is that it does not require the number of clusters to be predefined. So you do not need to tweak the number k of clusters or anything, but instead it just finds out the best possible clusters in your data. And it is also actually used a lot in outlier detection, because sometimes there is a cluster of data points that are too far from the other, and these are well, categorized as outliers. And maybe you can also use that in normal classification tasks in order to identify which of your data points or set of features are very non-relevant to your problem. Right. So DBSCAN requires a definition of what constitutes a dense neighborhood. So as we said here, so what's really the thing that makes this dense is that these similarities are small, like each individual similarity is small, but we still need to define how small we need them to be so as to consider the neighborhood dense. So this is not as simple as it sounds, maybe, but in scikit-learn they have found a pretty good way to do that. They define these two not hyper, they define these two parameters, mean, samples, and the epsilon threshold. So there is documentation in these two links I have here. You can check it, but the epsilon value is usually fixed, and you may need to tweak the mean samples parameter in some cases. But they have a pretty good explanation of how these two work, and specifically, I would recommend the second link because it contains. Wait. Yeah, I think that's the wrong link. I will fix it. Yeah, this should be the link. So here it says how mean samples and the EBS parameters work. Anyway, so this is a subset of the picture we saw before. So here we have k-means, agglomerative clustering, which we did not discuss and we will not discuss. I'm just including it here, so you will see that there are other clustering algorithms too. And then we have DBSCAN and GMMs. So, like we said, k-means and GMMs completely fail to classify the two clusters that are in this sort of circular, they follow this circular movement. And the same also happens with these semicircles. But on the other hand, with the graph-based or the density-based algorithms, we see that we are able to define that, this data point and the data point on the other side are similar. Just how we humans identify that these two are similar, just because they are interconnected through nodes that have good similarity scores. Right. Yeah, some other examples with pure noise and yeah, some other structures. Do you have any questions here? Yeah. Yeah, here in DBSCAN, maybe you could also notice that they have these black data points here. So these would be the outliers. these don't belong to a certain cluster. Okay, so this was the presentation. Um, don't have anything else to say. Maybe we could quickly go through the notebook if you don't have any questions. If you do have any questions, feel free to interrupt me, of course. So the notebook starts with some theory about clustering. Then you are using the cafe in Helsinki data, and you are implementing k-means clustering algorithm. So here is the pretty much what we saw in the pseudocode, but you don't have to worry about implementing this because scikit-learn already provides a solution. Um, yeah, so here you have an example of how to first define a class of k-means and then fit it on your data. And then you have all of these information in the parameters of the instance. Um, then the task here is to apply k-means yourself, and you should get something like this here. So these are the centroids that you should see, and here it's like there is an invisible line that separates the two clusters from each other. Then there is this way to handle local minima instead of global optimal solutions. So we have already discussed about that. You need to implement it and get an output like this. So here the smallest error is this assignment, while the largest error is this assignment, which makes sense even to the human eye, because this separation of two clusters is not so intuitive. And then there is the elbow method to decide on the number of clusters. And then there is the soft clustering, some information about how GMMs work. So this is optional material, you don't have to read it. And in scikit-learn you can use this class, Gaussian mixer class. Again, it has a ton of parameters, well, not a ton, but it has many parameters that you can use. Not so many attributes that you can use after you have fit the model, but the methods you use to do the training to find the clusters is the same, so you still use the fit method. Right, and then we have pretty much the same stuff as I mentioned. So this is a nice visualization of DBSCAN. Yeah, if you have any particular questions about the notebook, I would be happy to answer them now, because there is not much I could say for the notebook here. Yeah, okay. Yeah, after DBSCAN, there is also an example with of combining clustering with logistic regression, and there are some quiz questions. So yeah, I will stop the recording then.